光明哲访师范大学。
管基胜from National Taiwan University.
I'm Hasni from Cambodia Media School. Okay, thank you. I'm 黄州
信息好from Industrial Shanghai University.
I'm Tuzal from Pendulum University.
Hi, Jerry. Hi, ladies and gentlemen. My name is Henry Su, the team captain of iExplorer. This is my teammate Yu Qing Fang, Xie Xiaoyu, Hou Ruiqi, and Hong Pidi. Thank you.
Good afternoon. I'm Neil Liu from Vigo Senior High School, and I'm the captain of my team. This is Wang Shuoyu, Zhang Zhuyu, Hao Kaiqi, and Xu Chulei. So have a wonderful afternoon.
Honorable juries and fellow students, we are MD fresh from Lingdao High School. My name is Daniel, and he is Danny, and he is Yo En, and he is Pin Han. Yeah, thank you.
Okay, thank you very much. And reporter choose number 7, dynamics. So you have 5 minutes for the preparation. Each team please write down the name of the speaker.
Chairman. Ready.
Okay.
Hi, ladies and gentlemen. My name is Henry Su from Team I4. Today, I'm going to introduce problem 7B dynamics. Start out with the problem statement. A circular hoop rotates about a vertical diameter. A small bead is allowed to roll in a groove on the inside of the hoop. Investigate the relevant parameters affecting the dynamics of the bead. So the main focus of the problem statement will be creating a setup of a bead put inside a groove hoop and investigate relevant parameters and the effect on the bead dynamics. So here's my presentation outline. First, I'll start off with observation video, continue with theory, and equipment and setup, experiment and discussion, last ended with conclusion. So here's my observation video. As you can see in this video, the bead goes up when the circular hoop hits a certain speed. And if you look back at the video, you can see the bead drops after reaching a certain point. So based on these two main factors, I will introduce my theory. So the first theory, here are the Tablespoon Method, and there are two ways to mainly portray the dynamic of the bead. First is the conical pendulum method. Second is the Euler-Lagrange equation. And all two ways can find the equilibrium point of the bead, which I will mention later on. And you can just now think as the stable point you can see in the video. And the difference, however, the difference between Euler-Lagrange equation and the conical pendulum method is that Euler-Lagrange equation can find the equation of motion of the bead, which is crucial in the problem statement. So let's start out with the conical pendulum method first. In high school, we learned that a typical conical pendulum rotating with a rotational speed of omega. And if we apply that on frictionless rotating hoop, we can assume that the normal force is equal to the tension force of this conical pendulum. So we can later on solve the x-axis force and the y-axis force and the derive function, which is the stable theta point equals to r cosine g divided by r omega squared. How about Euler-Lagrange equation in this case? So in order to know the equation of motion, we have to first understand the kinetic energy of this movement, the potential energy of this movement, and lastly, we have to introduce a drag force because in real life there's a drag force created. So we can also another difference between conical pendulum method and Euler-Lagrange equation is that we can introduce this drag force. So after implying those three factors onto our Euler-Lagrange equation, our equation of motion looks like this. So in this equation of motion, we can find a very interesting thing, which is c dot double dot and c dot dot equals to 0, which means there's no c dot direction acceleration or c dot direction velocity. There should be a stable point. It's the same result as a conical pendulum method. C dot equals to r cosine g divided by r omega squared. And we also can notice that theta could also be 0 and pi, which also makes sense with the equation of motion. However, pi is not possible in the experiment since it's impossible for the bead to go on the top of the hoop since the design of the problem statement. So let's continue on with my experimentation. Here's my equipment and setup. I use hoop, bead, aluminum frame, variable resistor, and power supply. And then the thing I use to record my experiment video are GoPro and phone. And here are the software I use. I use Tracker to analyze the physical movement, Python to write simulation, and Jupyter Notebook to plot my plots. And here are my experiment outline. First, I will set up the camera and make sure the camera is vertical to the rotation axis. Later on, I'll set up my variable resistor and I'll conduct my experiment. Later on, putting those data into the tracker, and after analyzing those data, I can plot the graph through Jupyter Notebook. After plotting those graphs, I can later on use Jupyter Notebook and Python to write a simulation and compare my results with my experiment data. And here's my first experiment, which is finding the equilibrium point. Like I said, there should be an omega, which is a rotational speed, should be correspond to a certain theta. So we can later on plot a graph look like this, and we will call it a verification graph. And something worth noting is that this is only an illustration. It is not a proportional linear relationship. Yes. So how does that equilibrium point work with our theta against time plot in our experiment? As you can see, the B seems to have a stable point after a certain time. So we have to average that stable point. And that is where the equilibrium point is. So you can see in the video. When the beat goes up, it hits a stable point. We have to average that point, and we call it the equilibrium point. And how do we calculate that theta with a circular hoop in this case? First, we have to know that we put 1 centimeter distant paper inside the growth hoop, and we calculate the function of theta against x against theta using Python. Then we can get the relationship of x against theta. So the next time we can only output the x data in tracker to get the theta angle in this circular hoop. So my second experiment is changing the beat weight in our experiment. So you might wonder why I do that, because through the theoretical function, you did not see any relevant parameters or variables regarding to the mass of the bead. So I want to know whether is that correct or not. So I used 2 different sizes of bead. As you can see, it's approximately almost 2 times weight of the right is approximately 2 times for the right bead. So after calculating the data in tracker, we find that there's only a slight percentage of error created in different bead weight. So we can prove that with different bead weight, the equilibrium point should be the same. Then we can finally plot our purification graph, which is the omega against theta. According to our theory, and we use a radius hoop with 23 centimeters, and we can plot this purification graph. And however, you can notice that there should be an omega limit, which, since we don't want the theta to be an imaginary number, so we assume that the omega has to be bigger than a certain number, and we call this an omega limit. After calculation, we know that our omega limit equals to 9.323 radians per second. And previously, I talked about not making the theta point an imaginary number. And you might ask, what if I got the result of an imaginary number theta point? Then we have to first understand there are 2 types of equilibrium points. First is a stable equilibrium point. The second is an unstable equilibrium point. So the difference between these 2 physics models is that when a perturbation occurs, the one with a stable equilibrium point will return to its original stable status. The one with unstable equilibrium will not. So how does that work in our experiment and change the purification graph? As you can see in this theta against time plot, the lower plot is simple as the unstable equilibrium point, because when we give it a perturbation, it will go up and goes to its stable status. So later on, we can redraw and replot our purification graph. So the blue line, we can now extend it here, still consider as the stable equilibrium point. However, the red line represented here are the unstable equilibrium point, which is mentioned here. So later on, let's talk about the dynamic of the bead itself. Here, I divided the dynamic of the bead in 3 parts. First is the upmoving segment. The second status is the tumbling phase. The third status is the stable phase. So in the first upmoving movement, you can see in this video, when the bead is in unstable equilibrium and we give it a perturbation, it goes up. In the second stage, you can see that the bead tumbles. In the third phase, you can see that bead stays in its stable point. However, I want to focus on the third stable status first, because I talk about a lot of the equilibrium point part. You can see if I enlarge this part of data, you can see there are still a slight sort of simple harmonic motion around that stable point. So why is that? So first, we have to know we can include an alpha angle in our experiment, which is the tilting angle, since it's very, very difficult for us to create an exactly vertical circular hoop like the Droplet statement mentioned. So we can correct that alpha angle in our equation of motion, and we can create a new result, which is a new equation of motion. So we can know that some small simple harmonic motion frequency equals to this, and the amplitude of that small simple harmonic motion equals to this. We also could include the rotational effect of the bead. As you can see here in this kappa formula, we can insert the moment of inertia of the bead, and we can get a more precise radius of the bead too. So how do we put those 2 stuff in our simulation? Like I said, the reason that we use the equation of motion because we want to know the dynamic of the bead through time, right? So first, if I only plot drag and alpha in our experiment, the equation of motion will look, the C dot double dot acceleration will look like this. And if we add kappa and drag and alpha together, the C dot double dot is like this. It's hard to understand, right? So I plotted for you guys. You can see that if we do not include any of those, we consider this a particle mode, it will be a very strange movement. However, if we include alpha and drag, it will be very similar as the experimental result, which is the green line. It's a bit hard to see here. However, if we look on the red line, which I include alpha, drag, and kappa, it fits very, very well with the experiment. So here's the experiment data with 0.55 B, which the beta after calculating is 0.35. And this is the comparison result. And this is the simulation video against the experiment video, and this is the theoretical plot against comparison with experiment and theoretical. As well as for 0.7 B, it also has a very good fitting result. And this is also the simulation result against the real result. And here's a 0.8 B, and this is the result, simulation result compared to experiment result. So comparison with different beta, we can find that when the mass increases, the beta increases. This is very intuitional because when the mass increases, the index of drag increases, right? So this is very intuitional. However, the mass against the B does not have any relationship with alpha. So let's go into our conclusion. Our mass does not affect the equilibrium points, and F equals to BV is crucial in our equation of motion because it can readjust our dynamic of the bead. Last is that we find when the bigger the bead is, the bigger the beta is. Thank you. That's my presentation. Yes. Sorry.
Our juries and fellow competitors, this is the opponent from Team MD Fresh. So first of all, I would like to make some clarifications.
Yes.
So for the first question, so can you simply restate what are the parameters
So
that you changed?
basically, I changed the weight of the bead.
Yes.
And since I control the density of my bead, it also affects the volume of my bead. And second is the rotational speed of my bead. So basically, that's it. I use two parameters.
Rotational speed
Yeah.
of the bead or of the
Of course, of the hoop, right?
Okay.
I can control the hoop, not the bead. The
Okay.
bead, the
So
hoop.
you control the hoop through like the power supply, right?
Yeah, possibly.
Okay. I want to know how did you measure the friction of the ball? The friction of the bead.
Interestingly, you mentioned this. Since in our equation of motion, you see that we didn't include friction index, right? Since
So you just grab this based on your it is an ideal situation.
No.
Right?
It includes drag, but that drag is not considered as a friction, since that static friction don't do work in the Euler-Lagrange equation. So we don't consider static friction in the Euler-Lagrange equation. So we consider the one I consider, and which is the thesis I searched on the internet, consider H equals negative dV, which is the same formula as air drag. So,
okay. So just in my opinion, I think friction will also affect the result.
Yes.
Yeah, a little bit. Okay. How did you measure the angle? So I saw a part where you use was it Python or something?
You mean
the angle of the bead,
the angle
how
of,
much it went up.
okay, so like you said, sorry. So like I said,
Okay,
since
we'll continue the
oh, okay, thank you.
Yeah, thank you. honorable juries and fellow competitors. This is an opponent from Team MD Fresh. So after the presentation of the reporter, we would like to start off from directing. Next page, please. Summarize the presentation of the reporter. So first, for the theory part, the reporter uses conical pendulum method and also the Euler-Lagrange equation. So that is for finding the drag force and also the equilibrium point as well. Next page. So for experiment, so their setup, they use a hoop B and also they use a hoop and they also use a bead, and then they use a aluminum frame and also a GoPro attached on the top of the hoop, and a phone shooting from the side angle, and also a variable resistance. And for the parameters, so they change mainly two things. So the first one is the rotational speed, and the second one is bead mass. However, we listed also the volume of the bead because the volume of the bead is directly related to the bead mass. So for the data, they found out different points of the equilibrium point, and they divided them into stable and unstable. Okay. So for the reporter, some advantages are first, he clearly explains the phenomenon, and second, explain the mathematical process, and they also tell the relationship between the different variables. And for suggestions, they may consider more parameters, for example, the radius of the hoop. So for setup, some advantages are first, highly precise, and second, very accurate, and for the final one, resisted most of the parameters that might affect the result. However, some suggestions would be that they can try to conduct a 360-degree hoop for further analysis. And for theory, some advantages are that first, highly relevant to the equipment and experiment. For a second, it helps further analysis to get other parameters as well. And finally, they consider most parameters that might affect the result. Some suggestions will be that friction will also affect the result, so it should be also considered as well. And finally, for experiment and data, some advantages are that their experiment fits the problem statement. And second, the labels and graph are organized. And then, easy to show the relationship between the two variables. For a final one, their theoretical data is being provided and fits the experiment data. So overall, we believe that the reporter did a very good job. So this is the discussion structure of what I will be doing next. So first, I will make some more clarification of the theory, and then set up an experiment. And finally, additional parameters that might affect the result. Thank you. Okay, so back to the question that I asked previously, which was how did you measure the friction?
So like I said, since through the equation of motion, let me take this one from here. Like I said, static, since we assume and we observe that the bead is pure rolling, so it must be static friction, only static friction applied, the only friction was applied to the bead, right?
Yeah.
Also the rotational friction, but we don't consider that. If we only consider the static friction doesn't work on the bead. And so in Euler-Lagrange equation, you only can assume a drag force. This effect is also almost the same effect as the friction force, but it's not represented by the form of a friction force.
Okay. So one thing you just mentioned that is you said the state of the bead is rolling, right?
Yes.
Did you consider other states of the bead? Because there are several states of the bead. For example, sliding and also rolling.
Yeah, like I said, in our video, we can find that the bead is pure rolling. It's a little bit difficult to find, but we assume and in our theory and our experience, we can see that it should be pure rolling rather than sliding.
So what evidence led you to think that, oh, this is rolling?
You can see
the difference from what I see from this video is very clear. Yeah.
Oh, understand. I may improve my video technique
Yeah,
to
yeah.
show. Yeah.
I think you should better define whether it's
Yes.
rolling state
Yes.
or it is.
Yes, definitely. But just to clarify, in our simulation, we find that simulation result very pretty well with our final result. So we can just assume that it might be actually pure rolling. But I agree with your argument that if there is not pure rolling, maybe I can adjust my model a bit better.
Okay, thank you. Then, okay, I would like to talk about this graph a little bit.
Yes.
So I would like to ask whether what happened right here, because I noticed that there is a little bit increase. Right?
Okay. Very good question. So, like I said, this part represents the perturbation we give, and you might ask me that what kind of perturbation is that?
Yeah.
Perturbation can be caused by many reasons. It can cause by the little vibration of the motor, or I can manually give it a perturbation. So in this case, it's mainly because of the displacement, which may be the alpha angle or the tumbling of the motor, causing this little perturbation to create the opportunity for the feed to go up.
Oh, okay, so you just mentioned that there are how many types of perturbation?
There are multiple types. It could be anything. It could be.
And which one did you do?
We're not sure that which kind of perturbation it is. I think just by assumption, it might be that slightly tilted alpha angle. It also could be the tumbling of the motor.
Okay, so you're not quite sure.
Yeah, I'm not quite sure.
Okay, and can you please go up to page 26?
26. Okay.
I would like to know, like, what is this graph showing?
Oh, sorry, pardon. Because in some of the experiment, I just want to show that
it is like horizontally.
yeah, I take a picture of the horizontal. I shoot the hoop horizontally. However, the final result I show the data of the GoPro fixed inside the hoop. Yeah.
I would like to I want to know, like, what is the purpose of setting this camera, like, from the side view, because
Okay.
yeah.
Understand. So it's actually a very good question. So in sorry. As a matter of fact, I have did that experiment. However, the reason that I didn't actually put it on the presentation is because the camera angle is very difficult to fix. Like, how can I demonstrate a camera angle difference in here? You can see this is a rotating hoop, right? So our eyes, which is the iPhone represent here, are shooting directly to the center of the hoop.
Yeah.
So today, if the hoop rotates, it creates a slight difference, as you can see here.
Yeah.
This phenomenon can also be observed through a flat surface. And you can see that if you can also do a demonstration. If you put your hand in front of your eyes and you move it forward, there's only a very slightly or not much y-axis movement. However, you put your hand here, and you can see that if your eyes are the camera, there's a lot of y-axis movement. That's why I didn't at the end put the result of this. Yes.
So what results did you find after, like, doing?
So basically, I also fitted the result like this.
Yes.
However, you can see some unperfect plot. It's because when you're taking a rotating hoop vertically, you will create a time period that you cannot track. So basically, I have thought of method correcting that is using cosine function fitting. I use that function to fit that rotational effect and minus that y-axis correction. So basically, I assume that the y-axis variation is a cosine function. So I have to deduct that y-axis variation. So after deducting that, you can find the dimension of that is very small. There's only 1 degree error, and here is like 10 degrees. So minus means that is supposed to be the accurate data.
So it is very small, so you didn't want to consider it.
No, it's very big, but I mean.
It is not relevant.
Yeah, the reason that I at last didn't put on the presentation is because the analyze in the back is very hard to do, because you can see there are some empty effect. It's very
a lot of outliers.
Yeah, we're not sure this effect is created by the calculation error or the reason that since the lighting for the ball is very hard.
Okay, so basically when you're doing this experiment, so the footage from the phone is unnecessary, right?
Yeah. So we use GoPro as our main.
So maybe next time the phone might not be.
Okay,
Yeah.
understand.
Okay. And so back to the question I previously asked. As you mentioned before, there might be slidings, right?
Yeah.
And you also mentioned that there will not be friction.
No.
Yeah, it will be friction, but you will not be considering it
In the
to
equation of motion. In the
in the equation. So, but if there is sliding, so will there be dynamic friction? It will, right? But so
supposedly,
consider
yeah, you're asking me a normal physics question. If there's a sliding, it definitely is a.
Yeah, it is.
But here, like I said, I couldn't provide you a clear enough video demonstrating that it's a pure rolling. So I may improve my videotaping technique next time. But through our result, I think we got a pretty precise
precise
result.
Okay, so yeah. Can you please turn to page 51? Oh, I would like to know what is the rotational graph. Can you play?
Oh, okay. So, thank you for mentioning that. That is an VPython simulation. So, I assume my VPython camera angle is at the same as my GoPro. So you can see this red little dot here. Can the professor turn off the lights?
Okay, I would like to know what result did you get from this?
So we can find.
Is this relevant for?
Yeah, it's relevant. You can see these are the track of the trajectory of the beat, right? So this red point represents.
Then what is the x-axis and the y-axis?
So this is the GoPro angle, right? So this is the camera angle looking down.
Yeah.
So this is the VPython simulation is as same as our experiment video.
Okay, so you find you after showing this graph means that so this is your theoretical data and it matches.
Yeah. This is the trajectory, so that's why.
So this is your comparison, right?
Yeah.
Okay. So is this count as accurate?
Okay.
Well, what is your range of the accuracy?
Okay, very good question. You can see some a lot of graphs that quite frankly are not as well as taken. You can see this decay very fast. And this is the reason of the drag function. I don't want to change my presentation because it's too long, so I'll just write it here. The drag function is like this, right?
Yeah.
So the power of V should be adjusted because we don't know, this is the basic way of adjusting the drag function. So if we change the power of V maybe to, I don't know, a certain number, let's call it N, maybe I will get a more precise simulation result.
Okay, so this is also an improvement that you can do next time.
Yes.
Okay, so moving on to the point that I mentioned in my presentation, which is you should consider more parameters. Like, what do you think about it?
The reason I didn't, I did make a bigger group, but the reason I didn't do it is because I think the problem statement wants us to talk about the dynamic of the beat, and I spent a lot of time.
I remember the problem statement also say that you should find out the parameters that will affect.
Yeah, but the mainly reason affect the dynamic of the beat is the rotational speed, in my understanding. Yes, the radius of the.
Yeah, I'm just suggesting that you should also find out like the relationship of the radius of the foot and also the beat dynamic.
Okay, I understand. I will take that advice and improve myself.
Okay,
Thank you.
I think that is all for my questions. Thank you.
Okay, thank you.
Honorable juries and fellow students, after discussing with the reporter, there are some suggestions that I think they should next time better improve on. So the first one is what I just mentioned, is finding more parameters for the experiment. And the second one is when they mentioned that they use a phone angle to shoot the experiment. That might not be needed for next time as well. And then for another thing is that I hope that they can also define whether the state of the beat is rolling or sliding much more clear and much more explicit next time, because that will also affect the friction of the dynamic as well. Yeah. So I think that is the summary of our discussion. Thank you.
Good afternoon. So, first to the reporter, you investigated the angular velocity as a parameter, correct?
Yes.
So do you also think that that's the only parameter?
No. So just like what I just mentioned, there are other parameters like angular velocity.
Yes, but that's
is
the only one that he
Yeah. So that's why I suggested him to do more.
I also
Okay, so
changed
to
the
the
B
to
way.
the both of you,
Yes.
what do you think the angular acceleration will affect the dynamic of the beat? Because when it will eventually reach static position, correct? And the prompt says that we are investigating the dynamic of the beat. So how do you think the angular
I think that
acceleration
only
will
change.
I'm asking you
Okay.
first.
So you can like see the equation of motion. You can see there are C dot double dot effect. So you let's sorry. Let me turn the page.
So you can answer first.
Okay, so I think like the angular velocity will affect like the maximum height, but the dynamic one thing that it will also affect is maybe the state of the beat as well.
Yes, but I'm asking angular acceleration.
Yeah.
So as you can see, after dissecting the equation of motion, this is the C dot direction acceleration. You can see the result like this. It's quite complicated because you have to consider alpha and beta at the same time, and you have to since in Euler Lagrange equation, you have to when you want to put a force inside of it, it's quite complicated. So that's why.
Let me simplify my question.
Yes.
How do you think that will affect the motion of the beat?
So after seeing this equation of motion, we can find that this tumbling phase exists, and that small simple harmonic motion at the end of the stable phase also exists.
But my question is, what would the angular velocity, angular acceleration affect the motion of the beat? So let's say if we increase the angular acceleration, what will the beat do?
Oh, the B will have a higher stable equilibrium point. But that is a static result, not a dynamic result.
Yes, but
I think after you find out like the acceleration, you can know like the difference between the theoretical data and your experimental data. That is one key major fact that will affect. Yeah.
Okay, so
I can also answer.
to your answer, your angular velocity is changing because
Yeah.
I'm asking about angular acceleration.
Oh, angular acceleration. Sorry, I couldn't understand at first. Yeah. So the reason that I didn't consider angular acceleration is because the initial condition, which is our angular velocity, is in a constant. So we didn't consider adding the angular acceleration in our experiment because it will make this motion very chaotic.
Yeah. Thank you.
Okay, so dear judges and fellow debaters, I'm the reviewer of beat dynamics. And here's the prompt, and as we can see, the prompt clearly says that we need to find the parameters affecting the dynamics of the beat. So I'm going to start off by summarizing the reporter's report.
So they found that both the conical pendulum method and the Euler-Lagrange equation can find the equilibrium point of the motion. And they compared experimental data with the graph plotted from the differential equation using Python. And they mathematically revised the data obtained from the camera. They found that the equilibrium point is independent of the bead weights. And they revised the mathematical model by containing the tilt angle and the rotational kinetic energy. And their assumption is that drag force equals to negative BV. And the opponents, their approach is that they clearly summed up the report from the reporter, and they pointed out peculiar points during the report and discussed it with the reporter, and they gave many suggestions to the reporter. Their weaknesses is that the discussion lacks a central point and mainly focuses on two detailed problems. So my main question to both the reporter and the opponent is that do they believe that angular acceleration will affect the motion of the bead? And the reporter said it was not taken into account, but we'll consider this later. And opponent says that angular acceleration can explain the divergence of the theoretical curve and the experimental curve. But one thing that I realized is that the reporter showed me a theta double dot equation, but that actually means the angular acceleration, the acceleration of the bead. But the angular acceleration that I'm asking is actually the angular acceleration of the hoop itself. And in the reporter's report, they consider the hoop from accelerating from 0 to whatever their angular velocity is instantaneously. So they didn't consider the angular velocity and how it affects the dynamics of the bead. So we believe that angular acceleration can also be taken into account to explain the data and the whole model. So the opponent's question is that did they make sure that the bead is pure rolling and instead of sliding? And the reporter says that they said that they have they say it's pure rolling, but they did not show us footage of the pure rolling. So we think that they could see, like they need to have a video to prove that it's pure rolling, or they need to take the sliding effect into account. And the opponent asked that they should focus on more parameters and cut out unused elements. And the reporter says that they agree with that and they could improve in their future experiments. And we think that angular acceleration of the hoop is a very important parameter in this experiment. So by neglecting this parameter could strongly influence the whole model of the dynamics and of the bead. So we think that in future experiments they could investigate in the effect of angular acceleration of the hoop more. Thank you.
Here's my concluding remark. The opponent previously asked me, how do you make sure the friction of the bead and how do you consider an equation of motion? And then my answer is that because the static friction does not work in the system, so it would be suitable to assume the resistance force as a drag force so that we can solve the equation of motion. And was in the opponent's statement, they mentioned that they use Euler-Lagrange equation to find the equilibrium point. I think both the opponent and I has a consensus on that. And I also, aside from that, I also mentioned the equation of motion is derived from the result we got from theta of t. And concerning the moving state of the bead, sliding or rolling, we might suggest that we use pure rolling to simulate the motion and got a precise result. So it is suitable to say that it is a pure rolling in our experiments. And they also mentioned the y-axis deviation caused by the camera, so I shouldn't put down the presentation, and I agree with the opponent. We have consensus on that. However, it's just stuff that can make my presentation more diverse. So mainly my experience about GoPro attached to and fixed to the circling hoop. Later, we talked about the VPython simulation compared to the actual footage. So the value of that VPython footage is we can see the trajectory of that bead. So it is very similar to the actual world. And in theory, the opponent and the reviewer both mentioned I should change more parameters. But I think I agree with both of them. I should consider the ratio against the radius of the hoop and the radius of the bead and do more experiments. And lastly, the angular acceleration cannot be controlled by a computer program since we consider a constant angular velocity for the hoop. Thank you.
Thank you very much.
For a report,
Yes.
did you have tried or consider from different initial processing to release the bead? And the motion may be different.
I didn't try it, but I have seen it through my Python simulation program. Like the professor say, yes, it will. Professor is correct that it will
Maybe acceleration,
but
frequency.
acceleration can purely created by you can see you can see this through this graph. There's a small acceleration of the bead that can create by the alpha angle. That's why in the last of my presentation I compare alpha with the with my radius of bead. I mentioned that there's no specific correlation between two of them. It is just a case-by-case situation. If today my angular velocity of the hoop is very big, it will create a
Did you have release different processing and in your experiment?
No.
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 Okay.
Thank you.
So for the opponent, so you mentioned that you want to consider the factor of the friction or sliding.
Yeah.
So
Oh, okay. So
if you were them, what would you suggest them to do to analyze this?
Because for there are two states, right? Rolling and sliding, and because rolling will create like the moment of inertia of the rolling state of the bead will be larger, which means that the amplitude of the graph will be bigger at the end. So I think that's something that I didn't mention clearly because yeah, I don't want to say that rolling is extremely important. But what I will do if I were them, I will definitely I will also neglect the friction first because due to the formula. Friction should be neglected first, and then we can so that we can graph the theoretical data. Yeah, we'll basically do the same.
Right. For the reviewer, you suggest you need to consider angular acceleration of the hoop. So what would be your suggestion for them if you want to consider this for analysis?
I think we could track the angular velocity and with a relatively high sample rate, and we can calculate the angular velocity by that, and we can see how the angular velocity will affect the dynamic of the bead as the prompt.
You mean acceleration or velocity?
Acceleration. The angular acceleration of the hoop rotating.
Yeah.
So in this part, here the 0 point. Can you explain what is the 0 point here in the time?
Oh, so in the time. So it is.
It's when you start.
Yeah.
Okay. So what is you can see a difference here. The bead is going up at different time.
Yeah. Like I said, you need to create a perturbation for it has the opportunity to leave its unstable equilibrium. Like if it is a perfect environment and it is still on its bottom and it always stay in unstable equilibrium, if there's never perturbation provided, it will never leave that unstable equilibrium point. So this time difference is just we give different time we give it perturbation. So sometimes it goes by itself because, like I said, the perturbation created by the vibration of the motor. Sometimes I'm too rushed. I just wanted to give it a manual perturbation to let the beat go up, to make a more efficient experiment. Yes.
Okay.
We can get next door. first, the scores for the reporter are 8, 8, 7, 7, 9, and 8. Okay, and the scores for the opponent are 7, 8, 7, 6, 6, 7. And finally, the scores for the reviewer are 7, 8, 7, 7, 6, 7. Okay, thank you very much. Let's take a short 10-minute break. time will report.
Okay, good afternoon, juries and fellow contestants. Today we're going to talk about problem 12, Weber Force Pendulum. So here's our outline. We'll first talk about the problem statements, then the theory, experiment, analysis, and that's the conclusion. So first, let's take a look at the problem statements. A Weber Force pendulum consists of a mass hanging from a vertically oriented helical spring. The mass can both move up and down on the spring and rotate about its vertical axis. So I wanted to investigate the behavior of such a pendulum and how it depends on relevant parameters. So the thing that phenomenon is moving up and down and rotate these two points. And the discussing point is the behavior, which is moving vertically and rotating horizontally, and the following relevant parameters. So this is the problem statement demo. So as you can see, this is a Weber Force pendulum, and you can see that it's moving up and down, and both vertically way and horizontally rotating. So first, let's talk about the theory. So F equals to M, and the differential x on 2 times equals to minus kx plus epsilon sigma, not theta. And I is times 2 theta to dot, and equals to minus delta theta plus epsilon x. And after some mathematical simplifying, we can define x as ax cosine omega t, and theta equals to a theta cosine omega t. And omega here means the normal known frequency. And the ax here stands for the period with the vertical motion. And the a theta means the rotation, the period of the rotation movement. So next, we can use this kind of the equation, and later we can divide it by cosine omega t and make this. So next, we wanted to find the solution to ax and a theta. And we know that it has at least one solution to this equation, that is 0, 0, of course. But if ax equals to 0 as well as a theta, it will not fit our experiment, because if the period equals to 0, it will not oscillate. So there must be other solutions to the equation. So we use this to find the solution to ax and a theta. And under ideal resonance condition, which is more similar to Weber Force pendulum, we substitute omega s is approximately equals to omega theta equals omega 0. So we can find the solution with omega 1 squared equals to this, and omega 2 squared 2. So, and next, we define x as ax1 cosine omega t plus ax2 cosine omega t, as well as theta 1. It's because we use the linear combination to define this. So after some simplifying, we can find out the ratio between a theta 1, ax2, and ax1, a theta 2, and ax2. So we can put this into the top, the equation on the top of the PPT, and we can find the initial condition of the equation of motion. So here's finally we can get the value of ax1 and ax2, and we can put these two values into the linear combination equation, and we can make this of the equation of motion of our Weber Force pendulum in our experiment. So now let's talk about our experiment. So the first parameter, we changes the different spring. So the left one is the big one, and the right one is the small spring. And next, the picture on the right hand side is the pendulum we use. And the red things on the top and the green thing on the bottom is the clay. We use it to changes the length of the pendulum. So experiment 1, we changes different spring with different K and delta. So we create a Weber Force pendulum here. So as you can see, the delta is different with the big spring and small spring. Also the K is different too. So when it is 20 centimeters for the pendulum stance, you can see it's not really coupling right now. And this is a spring 2, and it's not really coupling right now too. As for 27 centimeters, it's not really coupling, and we just read this as not fitting the theory. And this is spring 2. Obviously, it's not coupling, and it's still not coupling too. So we can find out that a different spring with different K or delta isn't the main parameters for our Weber Force pendulum. So next, we changes the depth of the pendulum, which is changing the moment of inertia and also increasing the moment of inertia. So when it is 27 centimeters, as you can see, it's now coupling down. And this is theory line. We will later talk about the theoretical data and the experimental data. What's the difference between them and why? And this is 34 centimeters, and it's coupling right now too, and the theory one. And experiment 3. So experiment 2, we know that you can see that 34 centimeters and energy transfer isn't really fully than the 20 centimeters one. And as you can see, its specific I will give the right Weber Force pendulum, and it is 27 centimeters. So next experiment, we changes x0 and theta 0. So when it is 27 centimeters where it is rotating, our x0 and theta 0 means initial movement we give it. It's like we just begin it with the rotating motion, or begin with the vertically moving motion. So here's the rotating for 27 centimeters, and you can see it's coupling right now. And this is a theory line, and we'll later discuss this. And this 34 centimeters for rotating, and it's a theory line. So as you can see, in the theory line and our experimental data is a little bit different. And we calculate the T, experimental T, big T, and the theoretical big T, which is 8.44 and 8.55. And the differences between them is 0.11. As for the small t, which is this, and the big T is this. So the small t for experimental data is 1.73, and the theoretical small t is 1.71. So the differences between them was just 0.02, and same as this one. As you can see, the big T and the small t, the difference between them is really different. You can see that the big T experimental data and theoretical data is really different, have a really big differences. And the small t, just a little bit different. So the reason why we will explain right now. So here's the form of all of our data. So big T has a really big differences, but small t has a really small differences. So the reason why is like this, we assume this mathematical way to explain it. So under ideal resonance condition, we substitute omega s is approximately equals to omega theta and equals to omega 0. And we just taught it in our previous presentation. So we can get this one. And next, but in fact, in the experimentally, we just can't simplify this and substitute the omega s is approximately equals to omega theta and equals to omega 0. So in experimentally data, you can know that this. We can know that omega 1 squared minus omega 2 squared equals these things. So you can compare the resonance condition and the experimental condition, and you can see that there is a small differences between them. That is these things. So that is to say, when omega 1 squared minus omega 2 squared become bigger, the t will become smaller, and that is fully can explain the differences between the big T and the small t. So here's our conclusion. More similar to Rebound pendulum, we define omega x is approximately equal to omega theta. And equation of motion, we just put here to let you review it. And the next one is the normal mode frequency, which is we just discussed. Ideal condition, experimental condition. So when here is bigger, then the t will be smaller. So that is to say, the big T of theoretical data will be bigger than the experimental data. Thank you.
Dear honorable judges and co-debaters, I'm the opponent from Taipei Legal Senior High School. So I have a few questions for the reporter. So can you please turn to page 5? Okay, so page 5. I would like you to clarify why is these two omega the same? Are the normal frequency of the rotation and the vertical translation the same?
I think normal mode frequency is viewed as all of the movement.
I believe that the normal frequency of a spring, whether it's torsional or vertical translational, I believe that these two should not be the same omega. Because you just mentioned different period of your like rotational motion and vertical motion, right? So I'm wondering why are these two different since you derive all the equation in the presentation from these equations.
Oh, we have done many experiments, and we just wait until the omega is the same time with the x and the theta.
Okay, I'll continue this later. Please go to page 7. Okay, so why do you substitute those two angular frequencies?
Oh, you mean this?
Yes, why do you substitute those?
Oh, because when the omega n is approximately equal to omega theta and equal to omega 0.
Okay, that's continuation. dear fellow debaters and honorable judges, I'm the opponent. Now I'm going to talk about the opposed vote from Wilberforce Pendulum. I'll start off my presentation from the reporter's summary. So the reporter tried different spring type, but found that it is not the main cause of the it is not the main parameter affecting the phenomenon. And they try to change the initial position, whether it's the vertical position or the angular displacement of the mass. And they try, by what I know, I think they try to change the moment of inertia of the mass they have to fit their theoretical curve. Now, the parameters include the spring, the length of the pendulum, and their initial position of the mass. Now here's the reporter's conclusion. They concluded that the period of the oscillation in this motion is larger than the period in the experiment. And the omega x is approximately equal to omega theta in their experiment. So here are some strengths and weaknesses of the reporter. So he showed us clear stats for the derivation of his formula, and he gave us many experimental data so that we can understand the experiment clearly. However, he lack of a clear theory of why the rotational motion will be translated into vertical translational motion, and vice versa. And also he did not account for the energy transfer from the rotational kinetic energy to the vertically translational energy. So, and he did not mention the relation between the rotation and the vertical translation. Now here are the points to be discussed. So first I would like to understand what by omega, what does he mean in his equations. And then I would like to understand the relationship between the translation and the rotation. And I would like to also understand why does the phenomenon start, since if you pull the spring to an initial position, why would it start to rotate? And I would like to start my discussion now. Okay, so continuing our discussion, let's go to page 7. Page 7, okay, thank you. I still cannot understand why would you first assume an ideal resonance condition and substitute omega x and omega theta.
Okay, so when the omega x is approximately equals to omega theta and equals to omega 0, and at this time it will fit the ideal resonance condition, right?
Yes.
And at this time the energy transform from rotating to vertically will be the most efficient.
Oh, okay. So in your experiment, you experimentally try to make the omega x and the omega theta equal to each other. Is that what you do in your experiment?
Experiment.
Like, this is your theory, right? But I mean, by definition, we know that omega x is related to the spring constants and the gravitational acceleration. And we also know that this is related to the torsional constant of the spring, correct? And so why does it look like that? Since
Well, this is ideal condition, and we just compare the theoretical like this and our experimental
okay. So
data.
we also okay.
So in our experiment, this is not really like this.
Oh, okay. So let's go to page 5. So are these two omegas different, like what you mentioned in the next page? One is omega x and one is omega theta.
Yes.
Okay, so these are actually different. So let's talk about this phenomenon itself. Okay, since the problem says that there will be some relationship between the rotation and the vertical translation. So what do you think is the main reason that causes this phenomenon to happen? So if you pull the string, why does it start to rotate?
Well, we start when you pull the string,
Right.
and so you start the string with vertically movement. So
Yes.
it will rotate at first.
And it won't
So
rotate.
so it will move vertically at first, and then the energy will gradually transform to rotation motion.
Yes, I know the energy will transfer, but I'm still confused why the reason why the energy transfers. Because if you pull a string, it won't rotate, right? Why does it start to rotate? I'm curious about the starting of this phenomenon.
Because it's moving vertically, so the energy will, if it doesn't rotate, so where will the energy go?
It can just continue to oscillate vertically.
No, but in our experiment, the spring will gradually become stable. It will not keep just oscillating like this.
Okay.
So it means there is energy transfer from vertically to
Okay,
rotation.
so there is energy transfer. But I believe the main reason for the energy to start to transfer from vertically oscillation to horizontal rotation is that when you pull a string from its initial equilibrium position, it's slightly unwound. So when you pull a string, there's actually an angular displacement on the string, and because the string has a proportional elasticity, therefore when you pull a string, there's angular displacement, and that's the reason why it starts rotating, I believe. So I suggest that you can. I think the prompt says that you should include this in. You should investigate in the phenomenon. So I believe this is a great point to discuss in your report. Okay, so the next thing is the prompt also asked us to ask the reporter to include relevant parameters. So what parameters do we use throughout this experiment?
Experiment 1, we changes the different K and delta. And
Okay.
experiment 2, the length, which is depending on the moment of inertia. And experiment 3, we changes the initial movement, vertically or rotating.
Okay, so you have the initial position and the moment of inertia. So are you changing the moment of inertia in order to find the best spot for the energy to transfer between the
Yes.
rotation?
Of that
Okay, so
experiment.
throughout the
Of that experiment.
okay, then so this is your, like, how do you change your moment of inertia throughout your experiment?
Oh, we just, because this play, I said it's in this play, so we can make it longer or shorter just because it's play.
Okay, so
And the mass of the pendulum will
then is your moment of inertia measured or you calculate it?
calculate.
As you mentioned, this is play.
Yeah.
Right. Oh, okay. So how do you ensure that the mass distribution in this play is even? Because you use this to calculate the moment of inertia, right? So the distribution of the mass throughout this play is really important, correct? So how do you ensure that the mass is distributed evenly in that plane? And is there any spot here or some there, and is it already always the same?
I didn't know your question. You mean the red
So
one?
one of your parameters is moment of inertia, right?
Yes.
And you calculate the moment of inertia and you identify different moment of inertia under experiment. So how do you determine the moment of inertia of this? You calculate it, but how do you ensure that the mass distribution of this is even?
But we consider the moment inertia is has nothing to do with the mass between this two plane.
Yes, it has nothing to do with the mass of the two plane, but
Yeah.
the distribution of the mass actually influences the moment of inertia. So the further the mass is distributed from the center, I believe the greater the moment of inertia is. Okay, so
Well, we measure the length. Yes.
oh, you measure the length and calculate it.
Yes.
So can you go to your the page where you show the discrepancy between your theoretical data and your actual observed data? Okay, so do you think that so is this so this moment of inertia, did you calculate it or did you measure it?
Calculated.
Oh, and you try to move the clay into the clay to fit this moment of
Yes.
inertia.
To
Okay.
20 centimeters.
Then why do you think there is this discrepancy, like between the theoretical data and the experimental observed data?
Well, we just calculated T, we didn't do this.
Oh, but I thought you tried to calculate the moment of inertia using the theory. So let me have a suggestion here. I believe that if you try to measure your moment of inertia with more precision and ensure that the clay is distributed evenly, I think you can fit your actual curve to the theoretical curve. So that's definitely an improvement. And next, I would like to move on to the energy transfer.
Which page?
I'm still not referring to any pages yet. So as the spring goes up and down, and as the spring rotates, the energy is transferred from the translational kinetic energy to rotational kinetic energy. Okay, so as I said, the energy is transferred because there's this unwinding of the spring during when you pull the spring, when the spring is in translation. So have you investigated how the two phenomena are actually related to each other?
What do you mean?
By that I mean, have you actually experimentally do you experiment on how the spring, how the translation of the spring is related to the rotation of the spring?
No.
Okay, so I believe that there's some improvements there that you can do. So and okay, so you have your observed data. Oh, this is your experimental data, right?
Yes.
And can you explain why does the time displacement decrease over time?
Because we just consider two motion, right? Just vertical and horizontal. Yes.
Yeah.
But in fact, they will just have some other motion, like some wiggling or something. So there will wiggle become smaller.
Oh, so perhaps this decrease in displacement is because the energy is lost to perhaps swinging of the pendulum.
Or some other motions.
Oh, okay. So I believe that if you account that in your theoretical model, it would be definitely an improvement. Next, I would like to go back to the prompt. So the reporter experimented the prompt, the question. So I believe that the reporter fulfilled his experiment and.
Sorry, the time is up.
Okay, so I believe the reporter fulfilled his experiment on investigating this phenomenon, but however he didn't actually consider how the spring starts its rotation if it initially translated in its length. And also I discussed with the observer about the energy transfer during this whole phenomenon. However, he also did not have clear answer to that. But the reporter did have some great point where he changed the moment of inertia to try to investigate the relationship between the moment of inertia and the behavior of the pendulum. And what I would suggest is that he can improve his experiment by including more for instance, the energy loss to swinging in his experiment, in his mathematical model to get the experimental data better. Thank you.
Any questions from the reviewer?
Okay, I'm the reviewer today, and thank you all for your amazing discussion, and I have some questions toward the reporter. First, you mentioned the coupling term epsilon in your equation of motion, and I'm curious, what are the factors affecting the size of epsilon?
Epsilon is a constant.
Epsilon is a constant, so it's the same no matter what reverse pendulum you construct. Okay, I see. And the opinions of the well, I believe it has to do with the thing that actually made the spring up. So with different spring there is definitely a different constant, and you have to measure it. Okay, I see. Thank you. And a question toward the reporter. You mentioned you calculate the moment of inertia of the pendulum. How did you calculate it? And I'm curious. Are there any theorems you used in your calculation, like the parallel axis theorem, to calculate the moment of inertia of the clay box? Did you use this? Oh, okay, I see. And another question towards the reporter: what will happen when your assumption doesn't work? In which omega z, which means the longitudinal frequency, isn't equal to the natural frequency of rotation? What will happen when that happens?
What do you mean?
When the natural frequencies are the same.
See, I didn't get your point.
That's okay. Thank you. And to the opponent, what will happen when the two natural frequencies are not the same?
When the natural frequencies are not the same, I mean there must still be the energy transfer from the two types of motion. However, we can see it clearly. So I believe that they choose that natural frequency to demonstrate its phenomenon.
Okay, I see. Thank you. And since the problem statement asks us to investigate the behavior of a Wilberforce pendulum, other than vertical and rotational, do you think there are other motions in the Wilberforce pendulum?
I believe that when the spring is moving,
Yes.
and the rotation, there must be some airflow that makes it swing.
Okay,
And
I see.
that should be also taken.
Airflow that makes it swing. Okay. And a question towards the opponent. Sorry. You keep mentioning the energy transfer, and I want to ask, why can the energy transfer from longitudinal to rotational?
Well, when you pull a spring, then there's a torque exerted on the spring, right? And the spring wants to return to its initial position because there's an angular displacement that wants to.
Okay, thank you. And finally, towards the reporter, can you derive a special initial condition from your equation of motion in which there will be a unique motion pattern of the Wilberforce pendulum? Okay, and towards the opponent, do you think
that by unique, what do you mean?
you simple harmonic motions that can perform two independent simple harmonic motions? Do you think it is possible?
I don't think it is possible.
Okay, I see. Thank you.
Ladies and gentlemen, I'm the reviewer for Team iExplorer. My name is Matthew Payne for problem number 12, the Wilforce pendulum. This is the problem statement, which I think the focus is on both the two motions. And following is a summary and comment of the reporter. And the theory is that the phenomenon that the up and down movement and horizontal movement can oscillate at the same time is what we are going to investigate on. And laws to apply to are the normal modes of the Wilforce pendulum and the equation of motion of the Wilforce pendulum, from which we can derive other normal frequencies. And the experiment the reporter conducted are the different springs, masses, and the initial conditions. And the setup he used a single spring and a hanging mass. And following is the conclusion. The report states that when the two natural frequencies, Fz and F theta, are closer, the coupling effect will be better. And the beat frequency is equivalent to the difference of the two normal mode frequencies. Next is the comments for the reporter. I think that the pros for him are the well-prepared presentation and the full of theory. However, I think there is a deviation between the experimental data and his theory, and he should answer the opponent's question more clearly. Following is the summary and comment for the opponent. The advantage is that he has a well-prepared presentation and time management and precise questions. However, I think he could not catch the key point of the problem. And now is the summary of the discussion. First, the opponent asked the reporter, why could the spring start to rotate since we only give it an initial downward displacement? And I think it's due to the structure of the spring, since if we give it a downward pull, there will actually be a slight deformation caused by the structure of the spring. And the next question they discussed, how to measure the moment of inertia of the Wilberforce pendulum. I think since the two balls are hanging on two protruding ends, it will be suitable to use the parallel axis theorem to calculate the moment of inertia of the two independent hanging masses. And my question, apart from the vertical and rotational oscillation, are there more motions in the Wilforce pendulum? And the opponent answered that there might be a horizontal swinging that we can observe from the Wilforce pendulum due to the airflow. And I think, apart from that, that is caused by initial horizontal displacement and the forces on the connection points of the spring. And we can see some wobbling, as the reporter said in his presentation, caused by the non-homogeneous mass distribution of the Wilforce pendulum. And what will happen when the two natural frequencies, omega z and omega theta, are not the same? And the opponent says that the energy transfer will not be more complete, and the reporter said that it will not be so efficient. And what factors are affecting the coupling term? In my opinion, I think the coupling term is the efficiency of the energy transfer. So, how close are the two natural frequencies? How fast can they oscillate? That is the key point in affecting the coupling term epsilon. Following is the same question, which the reporter and opponent gave me a clear response. Following is the conclusion and the missed points of their discussion. I think they have the reporter can do more work on calculating the two motions. You can do that by calculating the potential energy of each peak, since there is no velocity in any direction. And we can observe, is the energy sum conserved? If it is not, where can the energy lead to? Could it lead to the other two motions? That's very worth discussing. And where's the source of damping? In my knowledge, damping can be caused due to air resistance and the friction at the connection points. And finally, other motions are still worth discussing because they can play a role. They need energy to oscillate. So if they need energy, then could energy leak from the longitudinal and rotational to the other motions? And I think those are the missed points of today's discussion. Thank you all for your time.
Okay, thanks for the opponent's discussion and the reviewers. So here's our concluding remarks. So main question asked, the opponent asked, why is the omega in the equation of vertical translation and rotation the same? So our answer is the definition of normal mode is not the same compared to the opponent's experiment. And next, opponent asked us, what do you change the moment of inertia and calculate? We measure the length and the calculate. And next, the opponent asked the relationship between rotation and vertical translation. Main reason is what? And our answer is it will be in vertical translation at first, then the energy will be transferred into rotation. We had also taken into consider of the theory mentioned by the opponent, but it's less relevant to the experiment. And remarks, the discussion was about the theory. relationship between different parameters, energy transfer, moment of inertia, and transaction for the opponent can make the question more clearly to have a more efficient discussion. And some factors were not needed to discuss, but not to ask irrelevant questions to use up your time. And the reviewer should try to slow down so that we will be able to understand the questions. Thank you.
Thank you very much. Is there any questions from the group? I have a question. The reporter, could you turn to maybe page 30? We have a comparison between the theory and the experiment. I think it's page 30.
Page
30. Any page with a comparison between theory and experiment. Yeah. Okay, my question is, how do you judge the description, if the agreement is good or bad? When you have these two curves that has no, and how do you quantify the quality of your theory or your
Because when it is fits this kind of phenomenon, it's really obvious that it's big and small. Just but in this figure, what do you mean?
Let me put it another way. You have omega 1 and omega 2, right? If you show the page with omega 1 and omega 2, the formula. Yeah. So have you compared this, your data with this? No?
Can I make some clarifications for the reporter? In his fitting graph and actual experimental curve, can you turn back to the page? Thank you. I can see some deviations of the frequencies of the two Wilforce pendulums in the data. As you can see in the theory, this page will do. As you can see, the wave peaks and the wave valleys don't match to each other, and that will mean a different wrong frequency is used. And in my opinion, I think that is caused by the wrong epsilon, because epsilon is very crucial to this experiment, and it represents the efficiency of the two energy transfers. So if you use the wrong epsilon, then this will cause a bigger deviation when the time goes further, and this is my opinion.
How do you
Well, I have the same opinion with the opponent, because when he's graphing this graph, he must input the constant epsilon, and I believe that if he modifies this constant, it can fit this graph better, because since the frequency of the theoretical curve and the actual observed one is not deviating with a too large extent, I believe it's not caused by miscalculation of either the moment of inertia or the spring constant, and therefore it must be because of the epsilon.
Any other questions?
So how do you determine the epsilon? You mean by fitting? Yeah, or view. Yeah. How will you determine the coupling constant epsilon? Yeah.
Well, if I were the reporter and if I were to do the experiment, I would first observe this data and try to fit the correct epsilon, and then do another experiment to see whether it fits the epsilon that I just fitted.
And I agree with the opponent that fitting is the most efficient way to calculate epsilon due to the too many complicated assumptions where the two natural frequencies must be the same to calculate the epsilon using the identity in the reporter's report.
In your last question, you asked, can you tune the initial condition to produce pure harmonic motion?
Yes,
And
and
what's your answer?
please, the reporter, turn to the page where you show your equation motion. Thank you. Oh, wait, next page. Next page. Next. Yeah, thank you. You can see AX2 is the initial displacement we give to the pendulum, is that correct? Yes, so if AX2 will be equal to a positive value of square root m over I, then this will be, wait, this is the wrong formula.
Just a short answer, please.
Yes, you can give if you give the pendulum the right initial displacements and the right rotational, it can make the coefficients of one of the normals equal to 0. And at this time, the pendulum will only perform one of the normals, either omega 1 or omega 2. Okay. Thank you.
Okay, thank you. If there is no more questions, then get the score. So the score for the reporter are 6, 6, 5, 5, 7, 5. And the scores for the opponent are 7, 7, 6, 7, 6, 7. And finally, the scores for the reviewer are 8, 8, 8, 8, 8, 8. It's good to see you doing that. Okay, let's take a short break. Stage of this. The reporter team choose department number 14. For speeches. We have 5 minutes. Write down the name. Yeah, please write down the name of the speaker.
这是一个指令，你这个比较近的方式是 based on particle。你这样概念越简单，对，你如果这个不是个 particle，技术上的问题，只是转速要提高，然后产生的能力一定要更高效，价值要提升，所以你才有办法。
As the recorder, please go ahead.
Good afternoon. I'm Glenn Wong from Viscous High School, and today the prompt that I'm going to be reporting is dynamic hydrophobicity. So first of all, let's look at the prompt. When a drop of liquid impacts a horizontally moving surface, the droplet may be reflected or not, depending on the speed of the surface. Investigate the interaction between a moving surface and a liquid drop. So for this prompt, we're going to be focusing on the speed of the surface as the main parameter. So this is the outline of my presentation. First, I'm going to be introducing the phenomenon and the theory, and then I'll talk about our experiment, results, and analyses. And lastly, I'll be summarizing it and conclusion. So here's a video from other people's experiment. As we can see, the liquid droplet is levitating on this surface, and the surface they're using is glass. And as we all know, glass is hydrophilic. So this is due to the motion, and I'll explain it more later. So my theory will be broken into two parts. First, the impact of the droplet onto the surface, and then the levitation of the droplet. So when a droplet impacts a surface, three different types of interaction might happen. First, a partial rebound, and second, deposition, and third, split deposition. And this is a experimental result from Chen's research. So the main phenomenon that we will be focusing on here is partial rebound, because this is the only one that after the droplet hits the surface, and the droplet will rebound so that it can create the hydrophobic effect that the prompt is talking about. But these two will also be discussed. So here is a diagram of how the levitation of the droplet looks like. So here's the droplet, and here's a horizontally moving surface. As we look closer, there will be a thin air film between the droplet and the moving surface. And this thin air film is what makes the droplets levitate after it rebounds from the impact. So we think that the thin air film has these two characteristics. First, the thin air film is a laminar boundary layer, and the reason that it's a laminar boundary layer instead of a turbulent boundary layer is because of a low Reynolds number. If we actually calculate the Reynolds number, and it turned out to be the maximum Reynolds number is 200, and in most situations, Reynolds number over 5 times 10 to the 5th power will become turbulent flow. So this is, we can think it's a laminar flow. And so the Lyft force from the thin air film could be explained by viscous stress. So air has viscosity, as we all know. And when the liquid deforms, it will have a stress acting upward to lift the droplet up, and we will get into it after I talk about my experiment. So for our experiment, we use a high-speed camera, a smartphone, and a DSLR. And we have a rotating plate, which is the moving surface, a stand, which we'll be putting our the droplet deposition thing, and a tripod to put the camera. So for the liquid, we use propylene glycol, which I'll explain later, and we use a needle to deposit the liquid drop. So why we use the propylene glycol is that you can see the density here, it's very similar to water. And it has a smaller surface tension than water, but a way higher dynamic viscosity than water. The dynamic viscosity of it is 57.571 centiploids, and these data are from Typt's research. We did not calculate it ourselves. So here's a comparison between the dynamic viscosity of the liquid we use, which is propylene glycol, and the dynamic viscosity of water. So we can see there is a huge difference between them. So here is our experimental setup. We use a DSLR to film from the top or a smartphone, depending on the day. And here's our rotating plate as a moving surface, a stand that will hold the needle that will drop the propylene glycol onto the surface, moving surface. And this is the side view, and this is the top view. So this is all the same, but you can see that the high-speed camera is over here, so that we can film our experiments, as you can see over here. So here's our experiment. And you can see that the droplet levitates on the surface. Let me punch it. So this is the partial rebound that I talked about earlier. And so if you want to know what happens when it's the other two, we can see here that this is what will happen when it's split deposition. So we calculated the Weber number for each trial, and we split it into tangential Weber number and normal Weber number. And we calculated the tangential Weber number using the tangential speed of the surface, and normal Weber number using the normal speed of the droplet considering the air drag. And here are our other things that you need to calculate in these. So let's talk about the drop diameter, since it is one of our limits of our model. We need to control our drop diameter in 0.002 meter to 0.0027 meter. And that is for a reason, because we assume that the drop is static instead of there's a flow. Because when there is a when the drop is not static, parts of it will touch the surface of the moving surface, and it will hold the whole drop and move with the surface. So that would make the whole situation hard to analyze. So by using a small droplet, which is in this range, because we couldn't make the droplet smaller, and it would make the droplet static, and that means we can analyze it more clearly. So for the levitation that I talked about after rebound, we need to reach these two conditions for the levitation. First, the normal velocity needs to be 0. That's why you need a rebound. And when it reaches the top of its rebound, the normal velocity will be 0. And when gravitational force equals Lyft force, and we will explain Lyft force later. But here's a graph of what I mean by gravitational force equal to Lyft force. It's like the upward lifting force is equal to the gravitational force, so it can levitate here. And here's our data. We can see here on the x-axis we have the tangential Weber number. On the y-axis we have the normal Weber number. And in our experiment we control the height of the releasing drop 6 millimeter. So this normal Weber number doesn't really affect the different situation of the drop, whether it's deposition, split deposition, or partial rebound. So here's another graph that's comparing the tangential velocity to the tangential Weber number. As I said in the start of this presentation, I mentioned that our main parameter is the tangential speed. So we must found a critical speed, right? So we found out that when tangential Weber number is approximately 60, that is where the drop will rebound and levitate on the surface, contributing to the hydrophobic effect. And when here, when the Weber number, tangential Weber number equals to 60, our velocity, a tangential velocity is approximately 1 meter per second. So that is the critical velocity that we found. But it's a range. And so for the lift force, we used lubrication theory to explain it. It's a balance of quasi-flow and quick flow, and it would provide the lift force. So what is quick flow and what is quasi-flow? So here's a quick flow and here's the quasi-flow. So the quick flow has a, and when we combine these two, it will provide the lift force that we want. And this quick flow has this lift force because the liquid going in here needs to be the same amount of liquid going out. And so that creates a pressure difference. And for the quasi-flow, it's caused by the pressure from the droplet, and these two will flow out, and when we combine this, it could have a pressure difference. So we could calculate the pressure gradient using these two equations, and this is from Sagawa-Kuchi's research. But unfortunately, if we want to know the h function here, and h is an xy function, and if we want to know that, then we need to use interferometric photography to find out the how thin is the thin air film, and we will need to calculate the thickness of it. So unfortunately, we're not able to do that because of technical difficulties. But we have this equation just demonstrating how, if we can measure it, how would the lift force be calculated. So for my conclusion, the droplet needs to reach an equilibrium which is 0 normal velocity, and we can calculate it by using Weber number and calculate the lift force, which needs to equals to gravitational force using lubrication theory. And here's our references.
Okay, thank you.
Hi, ladies and gentlemen. My name is Henry Su from Think Explorer. First of all, I want to thank the reporters who are working towards the presentation and the experiment as a whole. My first short question will be on how do you define a drop of water?
We didn't use water.
How do you define one drop of liquid you use in your experiment?
So as I mentioned earlier, this is the drop that we have.
Okay, so can you control the size of each drop of liquid? Let's say, yeah, how can you control that?
We can't precisely control it, but in our experiment, it's in this range.
Okay, and can you turn to page 31?
Okay.
What is the surface moving direction?
So actually, in this graph, I'm just trying to show the equilibrium of the force. And the direction of the moving surface could actually be this way or in and out.
Okay, understand. Okay, in page 12, you mentioned that the thin air film, and that is a laminar boundary. And you mentioned that is because the Reynolds number is in a number. How do you calculate that Reynolds number?
We calculate the Reynolds number using the equation for Reynolds number.
Yeah, but how can you calculate? How do you measure the viscosity of your, let's say, air?
So our experiment is done at 20 degrees Celsius. So we found the viscosity of air at 20 degrees Celsius and used that number to calculate it.
Okay, I understand. Thank you. cycle. Droplet. Why didn't you do that? Hi juries, fellow competitors. My name is Henry Su from Thinking Explorer. Today I'm the opponent of problem 14, the magnet of hydrophobicity. So this is the problem statement. The problem statement basically means with a horizontally moving surface and if you put a droplet of liquid on the surface, it will rebound and investigate this rebound effect and against the surface moving velocity. And here's the summary and comments of the reporter's report. In his report, he mentioned the theory about linear boundary and mentioned that the Reynolds number is in a certain certain range, so it can be considered a linear boundary layer. And the setup he used are DSLR, a needle, and a rotating plate. The parameters he changed are the speed of the surface and use different liquid and compare the liquid he used with water. The experiment he does are using different velocity of disk and the tangential velocity of disk because he's changing the rotational velocity. Okay. The results, unfortunately, they reported negative and conclusive and quantitative and conclusive results of his report and experiment. Some disadvantage and pros and cons about reporter's report. First, well-structured presentation, clear reference, and loud vocal voice. And some cons that the observation video doesn't match the problem statement, and lack of video to support his experiment and against the theory. Unclear emphasis in the conclusion, and unclear plot for his experiment. Discussion summary. My first question regarding to the theory is how do you calculate the Reynolds number since you need the viscosity and the velocity of the liquid. However, the reporter had told me the answer earlier, so we'll move on. What is the Lyft Force pointing up when the surface is going on the right? The reason that I asked the rotational direction of the rotating surface is because it is quite confusing. The force you drop is vertical to the moving surface. However, your moving surface, like the reporter said, can be going through the paper and or horizontally for the paper, so it's quite confusing. And what is the meaning of Rebound number in your experiment? So why do you use Rebound number, and what's that physical meaning behind that, and what's your result compared to your theory? Since you said that in some circumstance the Rebound number, the tangential Rebound number has to be 60, and why is that? And regarding to the setup, is the area of the disk the same as the surface? Since the problem statement mentioned and told you to use a horizontal surface, however you use a rotational surface, and so what's the difference between two of them? And you track the motion of the droplets, or is it trackable, so that we can observe the velocity acceleration of the motion? Since the problem statement wants us to discuss the velocity of the rotating surface against that droplet, so it's quite confusing. The report didn't discuss the motion of the droplet. And regarding to the experiment, how do you control the liquid droplet? And he didn't give me a clear answer previously. And what does the plot in page 35 represent? And could you re-emphasize the result you get from page 38? And are the conditions in the thesis fit with your experiment? Since you have cited lots of theses, so I assume that each thesis has its conclusion. So did all those conclusions fit well with your experiment? I'm quite confused. Now the different size of droplet, how will that affect the experiment, etc., different parameters? That's my opponent's step. Thank you.
Can you let me address something first?
Sure.
So we actually only tested propylene glycol as our only liquid that we use, because when the viscosity change, then a lot of different parameters need to change. That is definitely one limit of our model.
So for you said a lot of things change. For instance, what, the Wilbur number or something like that?
For example, surface tension.
Yes.
Dynamic viscosity.
Yes.
Density.
Yes. So that's what I'm curious about here. So today the problem statement says the movement or the droplet effect, or the droplet will rebound, is changing the surface, right? So why didn't you try different liquid, or it's just a technical difficulty or budget difficulty?
Okay, so I can show you here. Wait.
Okay, so just
so for the reason that you asked me, why didn't I use other type of liquid? So
yeah.
Here is a research by Barbarov. Okay, so they used a similar device as we did, and they used water as their liquid. So their drop diameter is similar to ours, but their tangential speed needs to reach 60 meters per second, and that is very high.
So it's because of the tangential velocity of the surface that you're facing. So okay, I understand. So okay, what's your assumption of changing, let's say, the viscosity or the surface tension of the liquid? Today, if I use oil, is it will it be easier to create that rebound phenomenon?
Great question. So in their experiment, they actually use silicone oil, which has a dynamic viscosity of around 50. But we think because silicone oil might be not very, the consistency of it might not be that consistent. So we chose propylene glycol, which has a similar viscosity, and we think that it could recreate their experiment.
Okay.
And for your question, we calculated the Weber number of these trial. So it is the, yes.
You understand? So, so have you had any experiment video showing that the rebound effect of the droplet? As you mentioned in your page 7, it is a partial rebound. So I didn't quite see the partial rebound effect. Can you emphasize that again?
Maybe use control, sir.
So this is the, let's to be clear here, this is a split deposition effect, right?
No, it's,
This is a partial rebound.
Yeah.
Okay, I understand.
Wait, sorry. So you can see that it bounced back.
Oh, I see here. So quite interestingly, through this video, we see some deformation of the water droplets. And like, as you mentioned, the reason that you choose a certain diameter of water droplets is because you don't want that let the water be too light, so it's very easy to deform. So how can you explain this phenomenon compared to your experiment?
Okay, so the deformation is actually an energy transform. As you can see here, the kinetic energy of the droplet when it hits the surface, and the kinetic energy will transfer its energy and make it a pancake-like shape. And therefore, the kinetic energy is saved in surface tension energy. And when the when the cohesion force pulls the liquid drop back, the drop will rebound.
Let's be clear here. This is a photo from the thesis, right? It's not your own result.
Yes, because we don't have the equipment to film this.
Okay.
But we can see in our earlier video, it's just not that clear, but it's very similar.
Okay, since we're talking about the drop itself, you mentioned that Wilbur number or the tangential Wilbur number is very crucial in your experiment, and it's the critical condition is around 60. And can you explain why? What's the physical meaning behind that?
Okay, so Weber number is actually a ratio of.
So today, if I ask you a higher Weber number will affect you a higher what phenomenon? What would you answer?
So a higher Weber number will actually means that the drop is easier to form into a droplet instead of coalesce with the surface. So a Weber number is a ratio between the surface tension force and the drag force. Oh, sorry. The cohesion force and the drag force. So its physical meaning is that whether the kinetic energy of the surface or the surface tension energy is dominant. So when the Weber number is high.
Can you turn to your graph to rhyme with your explanation, because it's quite confusing without experimental data.
Is it this one?
Yeah. So what's the relationship with this scatter plot? I'm quite confused.
So this plot is scattered. You can see the difference is not as big as this. It's from 6 to 9.
Okay, so quite interestingly, I noticed that the arrow bars here have a higher y-axis variation, and the points here with so those with partial rebound has higher x-axis arrow bar, right? Why is that? Why do you draw y arrow bar on the front of those dots and draw x arrow bar on the back? I'm quite confused.
If you come closer, you can see that there's both.
You draw both. Understand?
Yeah.
Thank you. So since we're talking about the rebounding effect, and you also mentioned that the thin airflow is crucial to recreate this phenomenon, right?
I'm citing this thin air film as the character that provides the Lyft Force.
So if without that thin airflow, there wouldn't be any Lyft Force. Is that what you're suggesting?
But there would be a thin air film.
But then my question is here: what's the main source and what's the main thing generate that airflow?
So it's the moving surface, and you can see here.
Do you have a relationship between your rotational speed against your generated wind speed?
So we assume that the wind speed is equals to the tangential speed of the plate.
Okay, here comes my problem. You use tangential velocity as a way of showing your airflow velocity, right? So tangential velocity equals to r times omega. Right? So it is used on a particle model. So how can that improvise to your experiment? Since you have a water droplet and the components of the water droplet is not, like you said, may not be even, or when it deforms, the mass calculation will be even harder. So how can you improvise that with your tangential velocity?
So as you can see here, we use tangential velocity because tangential velocity, the difference between using tangential velocity and using a, considering the rotation, the difference is under 3%. And
so do you think that if you follow the problem statement and use a horizontal setup, it will be better? Do you agree with that argument?
Not exactly. I think it would complicate the experiment.
Then can you show the page where you the first thesis you show when the droplet goes up? Can you show the page?
Okay.
then why I'm quite confused because the thesis that show here are using a non-horizontal surface. Why is that?
Because they also consider the tangential speed instead of considering the curvature of it.
Okay, understand. So, and can you turn to page 30? So, sorry for the inconvenience. I moved you back again. So.
You can go ahead and ask your question.
Okay, so I noticed there's a you said Vn is the wind speed, right?
No, it's actually the normal velocity of the drop.
The normal velocity of the drop. Why is that V equals to 0?
So it's actually my explanation why the droplet levitates and perform the hydrophobic phenomenon that we can see. So this Vn equals to 0 means that.
So what's the direction of that Vn? Sorry to interrupt.
So the velocity of the normal velocity of the drop.
Oh, so it's moving upwards, right, or downward?
It's moving downward because it's dropped from 6 millimeter and hit the surface.
So, just hypothetical question. Like I said, my opponent said, what would your prediction will be if you can track the motion of the droplet? What result will you get? Will it be sort of the as we normally drop stuff on table, sort of result of a coefficient of restitution? What result will you get?
I think it depends on the surface, and as you said, dropped on the table, and I think that is inaccurate because what we use is a glass, and glass is hydrophilic.
Understand. Thank you. So basically, in our previous discussion, we talked about some deformation of the water droplet. It's observed during the collision, and according to the reporter, it is the process of energy transfer. However, I think that it is also a key route to the energy dissipates. And also, the coefficient of restitution is desired or may be considered in this physics model. So according to the reporter, the airflow provides the lift force, but did not mention the relationship between airflow and velocity of the disk, since he mentioned that the problem statement focused on the surface rotational speed or moving speed, but he didn't discuss this relationship. And reporter cited the wrong information from the thesis. In the reference, they use cylinder instead of horizontal surface. Like the problem statement states, it wished to use a horizontal surface rather than a rotational surface. And it also includes that particle problem I mentioned earlier, which is V equals to R omega problem. Thank you, that's my remark.
So can you redefine the definition of Weber number?
Okay, so the Weber number is a ratio between drag force and collision force.
Okay, so in my understanding, the definition of Weber number is actually the inertial force, or the ratio between the inertial force and surface tension. So your definition might be incorrect.
Okay.
Okay, and which force will affect your result more? Is it the lift force provided by the airflow or the cohesive force?
I think there is a misunderstanding. So I use the lift force to explain why the hydrophobic situation will happen, and I use cohesion force to explain why the droplet will rebound.
Okay, so both force will occur in your experiment.
Correct.
Okay. How will Reynolds number affect the results?
So Reynolds number is just a way of me proving that our boundary layer is laminar instead of turbulent.
What's your opinion on this?
I'm quite confused since there's no direct evidence showing that the data of calculating Reynolds numbers, and quite frankly, since it's aerodynamic, it's pretty hard to observe, correct? But I wish the reporter can think of other ways to portray the aerodynamic effect rather than just showing the presentation with that thin airflow. It's quite confusing for me.
If you were not able to find out the thickness of the air fume, how can you find out the boundary region for Vn and Vt that best fit the condition for the droplet to levitate?
Sorry, can you repeat the later part of your question?
If you cannot find out the boundary region of Vn and Vt, how can you find out the best condition? Because there's no clear conclusion.
So the problem statement actually asked whether the droplet will reflect from the surface, correct?
Yeah.
So our calculation can find a number that when it's above that, the droplet will be reflected.
So from the data performed, do you think it's able to find out the boundary region for the best condition to reflect?
I'm quite confused. They only mentioned the wearable number limits, but however, there are multiple boundary conditions, such as you mentioned the thickness of that airflow, and
Okay, so it's no.
not complete enough for
Okay,
me
okay.
to
So
give
for
a
me,
conclusion.
I think maybe mention calculating the Weber number, the WEN Weber number for the normal force and Weber number for the horizontal force, and then combine them using a dimension that's maybe let's say x8. So then you can find out the relationship between the two Weber numbers.
Thank you.
Yeah, this is done.
So fellow delegates and honorable judges, I'm the reviewer from Team NC Fresh, and I'm going to review problem 14, dynamic hydrophobicity. So problem statement states that when a drop of liquid impacts on a horizontally moving surface, the droplet may be reflected or not, depending on the speed of the surface. Investigate the interaction between a moving surface and the liquid drop. So the key points I think should be discussed will be the speed of the surface and the motion of the droplet. So overview of the reporter. The advantage of it is it demonstrates the phenomenon clearly, although it shows the observation video from other people, and a clear theory and a clear definition of the droplet. They show three categories of the droplet, and a good schematic illustration was drawn, and error bar is being provided. And suggestion will be try to show your own observation video, and the only theory provided is a thin air film, and in my understanding that wouldn't be the main reason that causes the rebound. It should be cohesive force, and the theory explained is a little bit too simple and too many references and lack of their own research, their own experimental data, and didn't consider centrifugal force since they're using a rotating plate, and didn't consider air resistance, and their lack of parameters and lack of the trend line in the graph. And there is a weak conclusion that didn't help conclude the presentation and didn't show us more relationship between their chosen parameters. And overview for the opponent. So advantage will be the precise questions were being asked and demonstrates a clear concept of the problem statement and the presentation, the report. and catches on most of the critical problems of the experiment and conducted a well done and perfect discussion with the reporter. Suggestion might be he seems to have some misunderstanding with the report, and he can include own opinion on the topic. And the discussion 1, opponent asked define the drop of water, and the reporter said its diameter should be between 0.002 to 0.0027. So we disagree with the reporter since that the diameter will always be different and it cannot be controlled. So releasing a drop from a needle can help to control the diameter. Moreover, how can you measure a diameter? Like we don't understand the way how they measure the diameter of the droplet during its motion. And discussion 3, the opponent asked, can you explain Weber number? And the reporter said that it's a ratio between the cohesive force and drag force. Wait, no, the reporter answered that it's a ratio between the drag force and the surface tension. So we disagree with the reporter because Weber number is a ratio between inertial force and the surface tension. In section 5, the opponent asks, do you think that if you use a horizontal equipment, the experiment will differ? No, the results will be the same, answered by the reporter. And we partially agree with the reporter that the results will be the same if you consider centrifugal force and air resistance. So how will Reynolds number affect the result? The report said it was used to calculate airflow, and we agree with the reporter. So conclusion, a good discussion overall and major questions were being asked, and points missed out is didn't consider air resistance and centrifugal force since they're using a rotating plate, and a weak theory and future possible parameters weren't discussed between the reporter and the opponent, so they couldn't know how to maybe improve their experiment and the report. Thank you.
So my concluding remarks, first of all, the citations we have do not have to fit what the prompt addresses, since that's the resources to provide us and do our own experiment and come up with our own theory. And the Weber number is already dimensionless. So, and the normal Weber number does not influence our experiment significantly, as I said in my presentation. And we could try to improve our experiment by tracking the normal velocity of the droplet and present the data. But we actually calculated considering the air drag and using the release position of it. And for future experiments, we would like to measure the thickness of the film, and we include the thickness of the film only for the sake of the explanation. And another thing that I want to address is that they were talking about how my plate is rotating, but actually I think it fits with the problem statement because it is in fact horizontally moving. And we did not consider the centripetal force because we think it's neglectable, as I mentioned that the difference is under 3%. And overall, I know that the thickness of the airfoam is crucial for the levitation of the drop, but due to the technical difficulties we are unable to measure that. And in the future, we would really like to be able to use interferometric photography to measure the thickness of the airfilm and come up with a numerically theory that can calculate and explain the lift force. Thank you.
Thank you very much. Any questions? This looks like a difficult problem. Maybe let me just focus on one thing about the tangential velocity. Could three of you tell me how does the tangential velocity goes into some physical quantities that are crucial for the rebound?
So for the tangential Weber number, the tangential velocity is used to calculate that.
The Weber number depends on the tangential velocity?
It's one of the, it's in the calculation. Sorry. 27. 27. Here. here.
Sorry, can the professor?
How does the tangential velocity goes into some quantity that is crucial for the response?
So, if can my teammate answer again? Send me.
For the opponent.
You need to answer.
Yeah, only you can answer.
Okay, so in my understanding, that if you use if they repeat multiple times on the rotating surface, it will create a different effect for that tangential velocity, right? Because today, if you see the video in the reporter's report, he put the droplet very close to the rotating surface. And if today you move forward, your R changes, varies. So I'm quite confused, how can you define that droplet movement while your tangential velocity is continuously changing throughout different rebound? So that's my opinion about that.
So I think the tangential velocity can be put back into tangential Weber number. So if it will, in certain cases, that if the tangential velocity is fast enough, it will create a stronger air field, which will then levitate the droplet. Because I think in normal cases that the weight of the droplet will not be able to be lifted up by the air field because the lift provided by the air field was too small, and there are actually calculations that can prove that the cohesive force will be the main reason why it reflects. So I think if they can apply Vt back to Wet, they can find out the relationship between it, and if they can also find out the Wen, with Weber number for normal force, they can find out a boundary region where the height and the speed of the rotating plate is being considered, and they can gather the two information and know when will the droplet reflect the best.
I'm sorry, I feel like there's something that I need to address. So we use the tangential Weber number to calculate whether the droplet will reflect or not. And we mentioned the Lyft force, it's because we saw the phenomenon that the drop will stay hydrophobic, and we use that to explain hydrophobic. But for reflect, we use the tangential Weber number.
Any other questions? Okay, there's no question. Okay, that's the scores for the reporter. It's 7, 7, 5, 7, 8, 6. And the scores for the opponent: 8, 7, 7, 8, 7, 8. And finally, the scores for the reviewer: 8, 8, 7, 7, 6, 7. Okay. Okay, thank you very much for your hard work, and hope you have a nice evening.
Thank you.